Okay, so week 5 code should be in Canvas, so you should hopefully have that downloaded and up in front of you, so that you can kind of follow along while I'm going through it here. Um, so just like with every other week, there's a couple of packages that I have at the top because I know I'm gonna be using them later. So I'll run those to open the library for those, and then set the working directory and import the data. So at this point, hopefully you're importing your data file and you have roughly 189 variables, give or take. I think 187, 189, somewhere in there. If you're close, you're probably accurate. So on this week's homework, we're going to be bringing in a lot of feeling thermometers, 47 to be exact, and it'd take forever to have to code all of those variables individually. So we have a shortcut that we're going to be able to take, so that you don't have to spend all that time copying and pasting and changing the variable names every time you paste in a new variable, because this leaves a lot of room for error. Several of you on your homework had some problems where you weren't getting your recoding correct because you were copying and pasting the variable from a previous one that you recoded, and then you would forget to change one of the variable names somewhere in the code. So this kind of eliminates that headache. So far we've been using all these functions, but we haven't really made any of our own. And they all work the same. So here's the structure. You can name it whatever you want. And then this is the input here, and then you're going to have some lines of code and maybe some more, and then the curly brackets. So it's like X in the parentheses, and then you got curly brackets with all the code in there. And X is going to be like whatever you enter into a function. So if you were, say, doing the distap function, X is whatever variable name you're putting after in the parentheses after distap. So this, when you run this function, it's going to save this little bit of code as an object in your environment for you to call up later. And so then later on, when you do that function and then put in whatever you put in there, it's just going to run all of those lines of code just by running that one little name, which we saw the other day when we were in class. I showed you how you can just enter command and just run that function name, and then you can see like what's inside that function. If you come down here to the console, you can see the underlying code for what this function actually does. And then cross table. That's why I had that. Okay. I had the models, G models library up here, and I was like, we don't need that. Okay. So this one, you can see super long, lots of code, very complicated function. We're not going to learn to do anything like that right now. We're going to keep it pretty simple. So we want to create a function with the code that we'd be using to recode the similar variables. So all of the feeling thermometers have the same values for the different categories. So you're going to be using the same function over and over and over to recode all of those. We're not going to do the feeling thermometers because you have to do those for the homework. So instead I pulled some trait variables, and we're gonna do the same thing on those. And then you'll have to figure out how to apply this concept to the feeling thermometer variables. So there's like 8, I think, of these candidate trait variables. and they're all coded from 1, which is extremely well, to 5, not well at all, when talking about whether or not that trait describes whoever they're talking about. And I think the ones that we're pulling are basically just Biden and Trump. So the code that we would want to use to recode that would be this, something like this. We want to flip it because we want the higher variable to, we want the higher value to be extremely well. I think it's just more intuitive. Like if they have a high value for trust, then we think they're more trustworthy. So this other, like with the extremely well being low, just that didn't make sense. So we're going to flip it. So that's going to look like this. So we substitute X for the variable names up here. We're going to call it recode trait function, or recode trait func, and then function X, that's what we're going to end up feeding into it, curly bracket, the code to do the recode, and then end curly bracket. So if we were to run this, now you see it showed up in the console over there, and then just say function, well, function my data and if we were to just enter in like the variable name for one of those individual candidate traits and just run that by itself, it would apply that function, so apply that recode to the ANES variable. But if we have a lot of those, we want to do it to a bunch at once. And so for that, there's another function called lapply. This applies a function over a vector or a list to each of the individual items in the vector or in the list. So although the 8 variables that we want don't actually exist in a single vector in our current data set, they do in our code book. And this is why I stress that it would be good to keep your code book in Excel. So you probably already hopefully watched the video with the little tip on how to do the quick transfer of the variable names into Excel. That is so that you can come up with something like this. So in this case, these are the trait variables. This would be, the equivalent of the 47 feeling thermometer ANES variables. Then you want another column of whatever your variable name is that you're going to use in R in your data set as your second column. And then you want like nice R friendly column headers here. So we're actually going to import this trait code book is what I called it. I think for the feeling thermometer one, I said mini code book or something like that. Yeah, mini code book. We're going to import that as a different data set in R so that we can use those columns to mass apply our function. So import trait codebook. You see we've got 8 observations, 2 variables, so it brought those in. Now we can use the lapply function to apply our recode recode trait function to this vector. My code book ANES variables by reassigning the resulting values to a variable name. So then we've recreated and recoded 8 variables, or when 47 when we apply this concept to your assignment in essentially 5 lines of code. So if you remember that using this here, we can get or extract parts of the various data structures in R. So below, on the right, this here, we extract the vector my codebook ANES variable and concatenate it with my data so that we are telling it to apply this function to this function is telling R to apply this function to this vector in my data. And every time it does that, we want it to, on the left, we're going to extract the vector my codebook, my variable, and concatenate it with my data to form new variables for the values our function is generating. This, I changed some of these as I was switching this from the feeling thermometers to the trait variables. So if you run this, it's going to apply this function to this whole vector. And see our variables just increased by 8. Went from 189 to 197. We can check the work by looking at the range of our old, or actually I think I'd check a table. Our old variable versus the new variable. I had been looking at the range at first, but I didn't think it was as informative. So one of the variables is Biden strong, whether or not you think Biden is a strong leader, and you see everything syncs up. We flipped it, so 5 is 1, 4 is 2, 3 is 3, and so on. And then the negative 9s have been set to missing. Here's just another example of using a function as a shortcut. So this function, we're going to call this the frequency function. And this one is just going to apply this function to whatever. And we're going to make the distab function into So if you want to look at your variable names in this, we don't actually have to create a whole data frame if we're only talking about like the last 8 variables here. Remember, we can always extract items that we might want and make it into a vector. So this is just creates a vector of just those eight variable names. And then you can apply the frequency function to this vector. And it just pops out all of those frequency tables just all at once. So once you have all the feeling thermometers in your data set, you're going to have to do some t-tests and some ANOVAs. You're going to be comparing means, basically, which until Rick's lecture on Tuesday, you're not going to necessarily have a lot of background in the substantive piece of this, but I'm going to walk you through how to use the t-test function in R. So to start off, we're going to create a dichotomous variable for party ID just so that we have a dichotomous variable for some examples in here. So I just dropped the independents out as missing values. You wouldn't actually want to do that normally, but it's just a way for me to get a dichotomous variable to use as an example. The function for performing t-test is named pretty intuitively, t.test. You can run this line of code. Anytime you are curious about what a function does, this little question mark before it, in case I haven't said that before, we'll pull up the documentation over in this quadrant and kind of lay out the format and tell you what different arguments it will take. The t-test is pretty versatile in R. There's actually a few different methods that you can apply. We can use it to directly compare the means of two different variables, or compare the means of two different groups within a variable, like men versus women and gender. To compare the means of two different variables, we're going to use the function with the following structure. It's going to be x, comma y, comma alternative equals, and then either two-sided or less or greater. This is where x and y are just the two variables that you want to compare. And then the alternative argument indicates whether we're doing a two-sided test, a one-sided test where x is greater than y, or a one-sided test where x is less than y. So say our hypothesis is that Biden is rated as more honest than Trump. Then it's going to look like this. We're going to have t-test, variable x, so Biden honest, variable y, Trump honest, and alternative greater, because we're predicting that Biden is going to be more honest than Trump, so greater than. It's literally the exact same as flipping it and saying, putting Trump first and Biden second, and then saying just less. So if you run this, what you get down here is tells you what data it's looking at, gives you the t statistic, the degrees of freedom, and a p-value. So here, and then it also gives you the means of x and mean of y. So here, since the p-value is like way less than minuscule 0.001, we can reject the null on this and conclude that people do think that Biden is honest significantly more than Trump, or the mean is significantly higher for Biden than for Trump. If your hypothesis is just that they're significantly different, and you don't have any hypothesis as to which one is greater or which one is less, you can just drop the alternative argument. Anytime two-sided is the default argument here, and anytime you go with the default argument of a piece of a function, you can just leave it out. So if you notice, we have the same t statistic except for it flipped it, and that's because Trump is first and Biden is second. Degrees of freedom is the same, p-value is the same. We can come to the same conclusion. We've just run the test a slightly different way. Now, however, if our hypothesis is that Trump is rated more honest than Biden, so we've got Trump first, Biden second, and the alternative is greater than, we still have the same t statistic as we do up here, this 9.6197. Degrees of freedom are still the same. Now our p-value is different because it's applying the test differently. The next thing we're going to do is use it to compare the means of some outcome variable for the categories within a dichotomous variable. So say our hypothesis is that Democrats are more likely to say Biden is a strong leader than Republicans. I know these hypotheses are pretty obvious, but means the examples will work. So rather than entering an X and a Y value, we're going to use a formula. And the formula is going to look like this, where the dependent variable, and then it's going to have the little tilde, and then the independent variable. And this time we're only using the variable names, and then rather than the variable name, rather than my data $ variable name, and instead we're going to add an argument that says data equals my data. Also in this method, we stick with the default argument for alternative equals because it just makes things simpler. If you are curious about why that is, we can talk about it in class, but I won't go into it right now so that we don't confuse people who don't care. So we want to run this here. It gives you the same output basically, but now it's grouping the means within this party ID 2 category and giving you the mean of Biden strong for each of those two categories. And obviously, this is significant. We can reject the null. Of course, Democrats think that are more likely to think that Biden is a strong leader than Republicans. And this is only going to work, however, if we're comparing two means. So, two means here or two means of two different variables there. If we need to compare three or more means, R has an ANOVA function, also kind of intuitively named AOV. We can look at this documentation too. It's going to tell us all the different arguments that it'll take. And we're going to set it up very similar as the t-test, where when we were comparing the means of the outcome variable for the categories within a dichotomous variable. Except for this time, we're going to actually name this model so that it becomes an object in our environment. Because the output, if you just run this, it gives you the degrees of freedom, it gives you some residuals, it gives you the sum of squares, but it doesn't give you any p-value at all. So to get that, we're going to name it. So we're just going to call it M1 for model 1. And then run the summary function on that model. And now we get the p-value and the F statistic here. So now we know that the means of these categories within race, so we've got 4 different categories in there, are different, but we don't know which ones are different from each other. And Rick will talk about this a lot more on Tuesday. To be able to tell which groups are different from each other, there are some things called post hoc tests. And there's 3 that we're going to talk about, or 3 that Rick will talk about, and we can run them all in R, and they're all pretty intuitively named once again. So the first one is the Tukey test. That's actually Tukey HSD. And it's a function in base R, so you don't need to load any new packages for this one. And we're going to run that on the model. So there's a lot of good reasons for naming the model. So we need to do that to get the p-value. We need to do that to run the post hoc tests on it. So if we run that, we're going to get this output down here. That shows you pairings, and I think I gave some of you guys feedback on your homework to consider when you recode your race4 variable to drop the comma non-Hispanic after black and white. That's because these pairs get super confusing if you have like all those commas, and it's hard to tell which ones are grouped together. But this gives you a p-value for each pairing within the race category. So we can see here that Hispanics and blacks are not significantly different from each other. Other race and black are significantly different from each other. White and black are. Other and Hispanic are not significantly different from each other. White and other race are not significantly different from each other, but white and Hispanic are. So, mouthful there, but the other, what this does not do, and we'll ask you for it on the homework. So here's a function to get it for you, but it does not gives you the difference between the two means. So it gives you the difference in the mean for Hispanic and the mean for black, but it doesn't give you the Hispanic mean or the black mean. So to get that, you'll need to run this function here, and that, that's asking for a mean of this variable when this variable equals white. And then you have to be sure to add this, because otherwise it's just going to return NA, because it won't be able to calculate a mean if you have missing data in there. So the mean for white is 2.69 and some change. The SNK and Sheffey tests are the other two tests that Rick will talk about, and those actually are not in base R, so there's a package that we'll need to install called Agricole. I'm not going to run this because I've already installed it. You will get a message down in your console when you run this that asks you, I don't know, it asks you a question. I can't remember what it is. And then it says yes, no, something else. And just say yes. And you'll have to actually type yes in your console and hit enter. And then it'll finish installing it. And then you can run the library to open it. And then this is the format that you want to use for running these tests. Put the model in here. You put the independent variable here. And you have to tell it console true, because otherwise it does not show up down here in the console. I'm not sure why these operate like this, but they do. So that's just what we have. I can sort of explain what the output means, but we may want to talk to Rick about this a little bit more on Tuesday in class, because I can't remember. I'm not sure if all of this stuff is relevant or not. I think what is important is this here. And so what this is telling you is means with the same letter are not significantly different. So white is significantly different from everything else according to this, because nothing else has an A. Other and Hispanic are not significantly different from each other, because they both have a B. And then black is significantly different from everything else because nothing else has a C. And then, and that's for the S and K. For the Sheffey test, it's kind of the same idea here. Means with the same letter are not significantly different. So each of these tests you'll notice are coming to slightly different conclusions. So we'll wait for Rick to elaborate on that on Tuesday, because I don't remember which one is more accurate or which one to use in which circumstances. But that should be it. I'm going to post the homework too. So hopefully I wasn't like super confusing. I know at the beginning there, the underlying, what underlies this function here might be kind of confusing for you. So I imagine I'm going to have some questions about that on Tuesday. But for now, at least you all have seen it and kind of hopefully have a rough idea of what's happening and can maybe start to toy with the feeling thermometers in the homework, because I will post these when I post this video. And I'll see you all Tuesday.